to go. All right, so signals, the first thing you need to know is what is a signal, right? So just back to the basics. A signal, you know, you have a y-axis and an x-axis. A signal could be it could be analog, you know, it have analog signals, or you might call it continuous, and it could have discrete. Those are the two main types of signals. Yeah, so you should know those, at least these two: analog, continuous, and discrete signals. All right, so this here is an example of a continuous signal, continuous with time. Remember, continuous means that it has a value for all possible values in between a certain range. So 0.00005, it have a value for it, right? But discrete, it only exists at discrete points in time. So something like this. So this might be 1, 2, 3, and 4, and any values in between, it is 0. So there's an example of a discrete signal. Yeah, so continuous, discrete. There are different ways to analyze these two types of signals. All right, so any questions on that? Okay, good. So discrete, continuous, right? You should know that from a little statistics. So with that, there are some functions that you will need to be able to do on these signals. It's just like shifting it, expanding it, growing it, compressing it, and those sort of stuff. So you have to know those as you start up, right? So let's run through those quickly. So the first one is something called time scaling. And in simple terms, it's just f of b of t, right? So if b is more than 1, it will be compressed. And if b is less than 1, it will be expanded. You will appreciate this more when I go on to the math lab, right? But for now, just appreciate it. So example, if you have f at 2x, right, without even looking at it, you'll know this will be a compressed signal. Yeah? And if you see f of a half of x, this will be a expanded signal. So this will be expanded. And if you multiply by 2, it will be compressed. All right, so as I'm looking at it, you will know how it will look, right? And then the second type, or the second function you need to know how to do is something called a time reversal, which you should be familiar with. So that'll be f of minus t. Yeah, that's just a flip. So the end becomes starts. You're just flipping. Yeah, you'll appreciate this more when you jump to the math lab. Third one is a time shift. So you're shifting it left or right. So that'll be denoted as f of t plus or minus tau, where tau is what you're shifting by. So if tau is more than 0, it lag, and if tau is less than 0, it will be a lead. And you will appreciate this more when we jump to the math. So we did time shifts, time reversal, time scaling, and it's also one more, which is magnitude scaling. All right, so that is 2 f of x. Yeah, so so we could say, instead of putting 2, we could say a f of x, right? So if a is more than 1, so it will grow. Okay, just think of it multiplying the y values by a constant. If you multiply the y values by 2, the overall signal will just grow by a factor of 2. Yeah, and if a is less than 1, it will kind of shrink. Okay, you kind of half in it. So say a cos or a sine curve, and if you know the magnitude is 1 to minus 1, if you multiply this by 5, it should grow. But if you divide it by 5, it should shrink. Right? So the difference between shrinking and expanding and compressing. So don't mix up the two. Right? So you have any questions on any of these functions here?
No.
All right, so if there is a order of function operations, right? So as you see, so it have an order, just like BidMass or BODMAS, you have an order in which you could do these things. So you can't do it in any order. So if there were multiple of these in one, you can't do it in any order, right? So there's a order. So the first one you always do magnitude scaling first. Say a magnitude scale first. Then after the magnitude scale, you do your time scale. And after the time scale, you do your time reversal. And then the last thing you always do is your shift, your time shift. So you do flipping, expanding, or whatever, and the last thing you do is your shift. Because when you're shifting, the overall shape doesn't change. It'll just shift from one central point to another. So the order of operation. So there's something you have to remember. Depending on what you have, they will know which ones you have to do first, second, third, fourth, etc. and etc. Yeah? So any
Yeah.
questions on that?
No.
All right, so let's jump to the MATLAB. Let's jump to the MATLAB. I'm just going to share my whole screen because almost able. All right, so you see the MATLAB?
Yeah.
Should zoom in. Let us string the. All right. Okay, so I know you're not too familiar with MATLAB, but let's run through the code, right? So I have a fixed vector of x values running from -10 to 10, and I have 100 of them. All right, and the function I'm using is the sine function, which you should know. Sine x is just a normal sine curve, top 1, -1, 1 period, or multiple periods. All right, don't worry about the rest of the code, just now work with our sine function. So I'll just zoom in on that. So if we have a sine function, so let's just run through and you tell me what you think will happen. So sine of x, right? This just gonna be a normal sine function, which you already are accustomed with. Yeah? So
Yeah.
that should be easy. For the second thing, let's say we do a time scale. So we have sine of 2x, right? So this will be a time scale, right? So this will
Yeah.
fall under what we had f of bt. So remember, when b is more than 1, the signal will be compressed. So you have more in the same bucket. Yeah? But
Yeah.
if it's less than 1, it expands. So you have less. Remember, it's the same window you're looking at. So think of it as there's a window and you're looking at a tree. So you say you're looking at a mango tree, right? If you compress the mango tree to make it smaller, and you'll see more mangoes hanging on the tree.
Yeah.
Right, so it can compress. It's easier to look at when it compress. But if I was to expand this mango tree and make it bigger, look what will happen. You might only see the bark and a little piece of the top part. You might only see two mango hanging because I expand it. So you can see less mangoes or basically less of the tree. All right. So
Okay.
taking that same analogy, if I do sine 2x, I expecting to see more patterns of the sine curve occurring in the same window. Remember, the window not changing. Yeah? So
Yeah.
let's see. So let me see. So we have, so all I have to do now is just, let's see how our sine x will, just by explanation. So I run this, should come up any time now. All right, that's not, that's not, that's not, that's not, I think I got a mistake in the code. Yeah, so it's supposed to be, all right, while. All right, so I run that again. All right, nice. So right now we have this good. So remember that's full screen. So you're seeing the y-axis. Use
Yeah.
my so you're seeing the y-axis, right? And you're
Mm-hmm.
seeing the x-axis, and you're seeing this is 0 here, right?
Yeah.
So remember, sine is an odd function, so it wouldn't be symmetrical about the x-axis. Yeah? So you want
Yeah.
me to use cos for it to be
I mean, I could.
symmetrical? All right, no problem. So we use the sine. So let's look at the positive part of sine, right? So
Mhm.
sine x, you just have 2 going out. Fair enough?
Yeah.
So let's see if I could switch it to get 1. So that is sine x. Look at it. Look at the top. It's at 1. See that? And the bottom is -1. And
Mm-hmm.
right now we have 2. Well, kind of like 1.5 in our way, right? Okay, and then
Yeah.
here. So you have like 1.5. All right. If we wanted, yeah, we can go into that. But look at it. It's symmetrical. Well, it's the same on the other side. All right. So that's have a negative part and a positive part. But this is the task we're working with. This is just sine x alone, right? So let's see how
Yeah.
this going to change when we do some, well, when you play with it a little bit. So there you go. So we have sine x. So let's say we put that 2 here. Yeah. So let's see what happens. Yeah, if you see that.
Yeah.
So you notice what happened?
Yeah.
So the top still 1 and -1, and it's still 10, 0 to 10, 0 to -10, right? But you notice now you have more mangoes, you're compressing it. You have, think of a pillow. You hold the pillow out and you just press it down. You'll get more pillow in the same area. And you have more pillow.
Yeah.
So it's the same thing happening here. So you compress the signal, and this will happen when B is more than 1. Because remember this, right now, this is sine of 2x. Yeah?
Yeah.
All right. So, all right, no problem. So I catch it out. So let me see if I could get it. So I want to keep my sine x there. So what I could do, I could hold on, then I could copy this, Control C, Control V, and let me say 1. So we could go back up here now. Y1. If you have any problem with MATLAB, we could always come by me, right?
Okay.
I don't think I'll have any MATLAB to do now.
No,
Semester two,
I don't think
yeah.
anything for the semester.
So they kind of get away in our way. Oh, I plot it. Uh, so X. Did it plot 2 graphs? No, it didn't. See what going on here. Anyway, I ain't gonna stress out myself, but all right. So figure. So I need to put our next figure. Run it again. Last time. And all right, no, it's not giving me what I want. Oh, it plot 2. So why you gotta plot my thing like how I wanted, but anyway, whatever it is. Let's go back to your right. So that is 2x. All right, so let me just erase this. Obviously, not playing nice. All right, so I'll play around with this now. Don't worry. So right, so that is sine 2x, right? So we notice b was more than 1, so it compressed. All right. So guess what will happen when I half it? We think will happen when I half. So b is less than 1 now.
Right.
So,
It'll expand.
but when it expands, how it will look physically, you'll see more of the sine wave in the
You'll
same
see
box.
less of it.
All right, no problem, no problem. Let me see. Let me see that the beauty of doing it in MATLAB, if you cannot see. Right. So, oh, you gotta save it. Why does save again? Let's see this. Line 5. Add, oh, sorry. Add a semicolon. 5. semicolon. That's weird. Okay, no problem. Sure. All right. So I got any answer. So giving me two sides. Oh, because it now plotting the second one. Okay. All right. So you see how things just work out in a way that makes sense. So now I was missing a semicolon. That is why it wasn't working.
Oh,
So I could plot in it out so you could see. So this will be sin x semicolon. All right. And I can scroll along here now. And instead of making it blue, I could make it red. All right. Okay. So the red one is your normal one, right?
mm-hmm.
And the blue one is the one we changing, okay?
Yeah.
So look at it work out. So look at the red. You notice the red, it's half, we had say 1.5, right?
Yeah.
Well, as you correctly said, you have less of the sign in it, in the same box. Remember the box went from 0 to 10, right?
Yeah.
So that's, so you clearly see and you have less of it inside. We pull it back out what before. Nice, good deduction. So we notice as the under times given, right? So you notice
Okay.
that when B is more than 1, it compress. So you have more of it in the same like, window, right? Or the same allotted time. But if P is less than 1, you have less of it. All right, so that's for stupid purposes. Let me see what the difference is. So instead of half, pick a number that is more than 1.
3.
How much? 5?
Yeah, 5 goes.
No problem. Let me see. So what you expect if it's 5?
You'll see more complete revolution.
More,
You'll see
okay.
more detail.
Yeah, you can say more oscillations. Yeah, you can say that. Oh, yes, correct. Very correct. Yeah, way more. Remember the red is the standard, right?
Yeah.
Red is the standard. Well done. So now, what do you understand what time scaling is? Yeah, that is
Yeah.
all it is. If B is more than 1, yeah, you can press it. And if it's less than 1, expand it. Yeah, so how I used to think about it as is B is more than 1, which means I'm gonna get more oscillation. So I'll get more than 1 oscillation. And if it's less than 1, I will get probably half or anything less than a whole oscillation. Yeah? So more
Yeah.
than 1, I will get more than 1 oscillation. So more than 1 of what I already have. And if it's less than 1, I will just get less of what I already have. Yeah? But I time scale it. All right? So any questions on that?
Nope.
All right, let's see less. So the next one we have to do is on our book. So I can still open back this because I share any whole screen, right? So
Yeah.
we did time scaling just now, right? So we just understand how this does work. So the next thing we want to do is probably the most intuitive one is the time reversal. So the N will become the start, right? So let me see how that will work in MATLAB. So if we're doing that in MATLAB, let's clear this, right? So let's put us back to X. So we have this, right? So if I want to reverse this, I could just do this.
Mm-hmm.
That makes sense?
Yeah.
So we expect it. Where you think will happen when we slap that minus? Do not say go reverse.
It'll
But
look
what
like
where you go?
a reverse sine wave.
Alright, okay. So you okay, well we see. You have the idea, so you kinda have the idea as well. Wow, well done. Remember the red is your bench.
Mm-hmm.
Remember here it is your bench. Right? So how will it look really? Think of you rotate something 180 degrees. Well, 360 now, yeah, 360. You just rotate it 360. So think of the red. Let's full screen it. So you're taking the red, I literally just going around like that. So that's actually 180. So if you go 360, it'll end up where you start. So it's 180 going around. All right, so
Mm-hmm.
it'll literally just be the same signal. So the end will become the start. Yeah, that's literally what it's be. But all in all, it is just flip it, going around, going around. Is our reversal. It literally just reversal. Also, you can look at it on the using the x-axis and mirror line. You'll notice that it mirrors, right?
Yeah.
So it's a reversal. It literally just reverse. All right. So that literally is be. So this come here, this come here. It literally reverse in all places. This will come back at the bottom. It reverse. All right. But anyway, well done though. As a reversal, time reversal. Most intuitive one. So if you slap a minus next to something, it will reverse. Time reversal. And you should know the order in which that will come. Right? So that was time reversal. Any questions on that one?
No.
All right, so we just did time reversal. Sorry. So now we have to do a time shift. Right? Let's do the magnitude scaling and then now do the time shift, right? So the magnitude scaling, just as the word says, it will scale the magnitude of it, right?
Mm-hmm.
So that wouldn't be inside here anymore. That is outside of the function. Yeah? So any
Yeah.
number you see outside and being multiplied by the entire function, that's a magnitude scale. All right? So if I scale the magnitude of something, what do you think will happen? What will happen in the x-axis? Anything will change in the x-axis values?
No.
Right, correct. Anything will happen in the y-axis values?
The y-axis values will either increase or decrease
Right,
depending
but
on the
if it
magnitude.
is positive, what do you think will happen?
If it's positive, then it'll grow.
So you think it being minus or positive would change the growing or shrinking?
No.
All right, well, let me try it out and see. So we'll use 2, right? Remember, red is your benchmark. So with 2, we expecting the magnitude to increase by 2.
Yeah.
Yeah? Well, let me see.
Yeah.
All right, wow. Okay, nice. So we have this going on. Remember, the red is your benchmark, and you were correct. So you have 1 here. All right, and then you multiply the overall magnitude by 2, and you increase it up to 2. Well done. Yeah?
Yep.
Fair enough. Well, let me see if it making a minus, we're going to change something. Let me see. Look at that. What do minus do?
Okay, so basically like a combination of time reversal and the magnitude scale and okay.
Well, it probably did do a time reversal, but okay. I see in your thought process, and that will work for sine. That will only work for sine. Reason why
Okay.
is I don't know if you remember this. Sine. Oh, that's all. Let me make that more legible.
All right.
Sine of minus x is the same as saying minus sine of
Sine.
x. Yeah? So that is
Yeah.
why with this, you gotta say a time reversal. Because yes, it will still be a time reversal because of the sine rule. Well,
Yeah, but
this
it
sine rule
won't
here,
work for cos.
it will not work for cos. Yeah, some different will happen for cos. So you were correct. It is a time reversal and it did scale up to 2. So at this point is 0 and 0, 0, 0. But this point here is 1. So remember we have different orders. All right, so the magnitude scale is first, and the time reversal will be the last thing. So to scale it, it went up to 2, and then they did the time reversal to get it down. Yeah? So 1 by
Yeah.
2 is 2, and then they invert it. Fair enough?
Okay.
So remember, if you're using
Yes.
cos now, cos and minus x will not be the same. That will just be cos x. Remember, that is an even function.
Mm-hmm.
Yeah, so just be careful. I hope you're seeing. Yeah?
Yeah.
So you won't make the mistake just in case they bring cost and stuff. All right, nice. Well, what else we had to try? We had to try, we asked already minus, we got the minus. So you see if we use like a half or something. Let me see what got if we use a half. 0.5 fits. I ain't going to that 1 divided by 2. All right, let's see. Wow, okay, no problem. Remember the red is your bench.
Yep.
So where you seeing happening then?
The amplitude halved.
Yeah, well, basically, you can multiply by half. All right. Now let me try something stupid. I mean, that makes sense, right?
Yeah.
Because I mean, the red line, you're not gonna see one compared to zero. So it there, but it just not easily see. All right.
Mm-hmm.
But you
Yeah.
understand the idea of it. And if I
Yeah.
was to make it 0.600, well, what was my point by? Where's that one? 0.600. Plot that again. All right. Well, the game, the bread is your bench. Well, I mean, that makes sense because 0.6.
Yeah.
I want a big change. Let me put the zeros before the 6. Uh-huh. Stupidness. That will make sense. Now I reverse. So now the blue
Mhm.
extremely smaller because of the magnitude scale than the red. Remember, the red is your benchmark. Yeah?
Yeah.
Makes sense.
Mhm.
All right. Nice. So just like that we did, that's magnitude scaling, right? Yeah, makes sense.
Yeah.
Questions, no
Yeah.
problem. So the next thing we have to do is time shift. Yeah, just
Mhm.
as it will says, it's just shifted. All right, and just as you have it here, it's inside the bracket now, right?
Yes.
So that shift is like you're doing 2030 now. So you know
Yes.
sine 2 pi ft plus theta k. Theta k is similar to our time shift. But if
Okay.
you're dealing with cos and sine curves, it would just be like a phase shift. Yeah, shift. Yeah, phase shift. Remember, if you're dealing with cosine and sine, the x-axis will now be like degrees. So pi and 2 pi and whatever. So that will
Mhm.
be a phase shift instead of a time shift. Make sense?
Uh,
So it's the
Yeah,
same
that
thing.
makes
It's
sense.
just different words they use it. But let me see how that does work in the math lab. So some theory, right? So remember, is f of t plus or minus tau, right? So
Mm-hmm.
if t is positive, we're going to go in this direction. Well, if tau, sorry, is positive, it will go in this direction.
Yeah.
And if tau is negative, it will go in this direction. You gotta remember this.
Mm-hmm.
All right? Well, let me see. Let's see it. I like to see things. That is the best way to memorize stuff, right? So in our sine function, we could right here, because it's trig, so I can't put plus 2. That were wrong, right? So I had to get
Yeah.
them a angle. So I could say pi, that is 180, divided by 2, that is 90 degrees. So before we load it up, at positive, right?
Mm-hmm.
So we're expecting it to shift to the left,
Yeah.
right? And it's pi and 2, which is 90 degrees. So we're expecting it to shift 90 degrees to the left. Yeah? Remember, your
Yeah.
red is your benchmark, right? So let me
Mm-hmm.
see how this goes. All right, so we have our function. Let me analyze it. So the red is here, yeah?
Yeah.
See, and you notice that it shifts 90 degrees to the left. Now the blue.
Mm-hmm.
You
Yeah.
cannot look at where it started. So the blue starts in here and the red will start in here. So the red leading the blue. Well, no, other way around. So see they ready. But don't worry about it too much. You gotta memorize that. But for now, it shifts to the left. All right? Let me see what will happen if you make it negative. So negative means you're shifting to the right. And you're shifting to the right 90 degrees. Yeah, just as you said, correct. Red is your benchmark. You notice it shift, the entire waveform shifted to the right by 90 degrees, right?
Mm-hmm.
That is minus top. I remember that. Minus is to the right, plus is to the left. Remember. All right. Now we try something else. Instead of pi and 2, we try pi by 180, right?
Yeah.
Pow. What you seeing there?
Yeah. Kind of looking like time use. So.
Correct. So if you shift something 180 degrees, it kind of is the same thing as doing a time reversal. Remember what when I did You just turn it at 180 degrees to the next side.
Mhm.
The same thing you did. That's what you did. If you shift something 180 degrees, it does come across like you inverted.
Yeah.
Yeah, well done. You're connecting the dots. All right, so that's something to remember. But let me make it more pronounced. That one was too easy. You clearly could see. But it's minus, so I'm not going to the right. So if I say 3 pi, 3 pi, let me see what this will pop up. Wow, you think it'd make a big difference?
Nope.
It's again the exact same because I just shift it pi, pi, pi. So it should just gonna look the same. So we had to make something to make it look less of a reversal. So we can do that. Probably divided by 2. What that'll be?
Yeah.
Pi is 180. So like 360. You think that gonna make a big difference? 360 divided by 2 is not like, oops, what's going on there? Invalid function. Too much stress. Let me just put the
2 is
divide here. Let's see if those still
that's 2.
ah this. So oh wait, the brackets. Right. I was doing the correct thing. Wow, okay. MATLAB does have a specific way they want stuff, right? So right, anyway, yeah, back to our seat. So now we're looking at the difference, right? Remember you read as your benchmark. So I kind
Yeah.
of shifted the across. Let me see what I type in there. So that was 2 pi on 3. So that is 360 divided by 3. So that'll be like 120 degrees. So I shifted to the right. Make
Yeah.
sense? Because pi is 180. All right? And then that's where we go. Makes sense. Time shifted. Yeah? So any questions on those 4 operations?
No.
So time scaling, time reversal, time shifting, and well. So let's try to do multiple things at the same time. Ready for that?
Yeah, sure.
So instead of just doing one thing, like try to multiply by different things. So let's start with the normal thing. So you're seeing where we started. Yeah. So let me
Mhm.
do a time scale. So that'll be pick a time scale for me. Anyone?
10.
10?
Yep, 10 goes.
Alright, no problem. So if we pick a time scale at 10, where you think that will happen? How it will look?
You'll get like 10 complete oscillations.
Well, not exactly 10, but on the same way, you just get more oscillations.
Yeah.
Yeah, so it wouldn't be always be 10. Okay, it depends on how much in the interval they get. You'll just get 10 more we already have. Yeah,
Yeah.
don't say 10 more because that depends on how it's looking, right? If you have just
Yeah.
one waveform, you might just get 10 more, right? So just be careful. You can say 10 more patterns, 10 more current oscillations. But you're correct. Conceptually, you're correct, right? Right, so
Yeah.
that's our time scaling, right? So if we have to
Mhm.
add a time reversal to this, we'll have to add a minus over everything, right?
Yes.
That makes sense. Okay, cool. But this is runner. Let's keep eye on this tick. If that go red, let me know. All right, so we have our time reversal, we have our time scale, um, time shifts. Right, add a magnitude shift. Pick a magnitude shift from anything else.
Uh, 5.
Okay, no problem. 5. So we expect the magnitude to increase by 5, right? And then we add our time shifts. But our time shift will be inside here, right?
Mhm.
So that'll be what direction you go in?
Uh,
Left or
if
right?
we if we go in left, then we'll add. If we go
All
in
right.
to the right, we'll
Well, you
subtract.
pick one. You pick one. What direction you wanna go?
Uh, +7.
+7. So that will take me to the +7 will take me to the left.
Yeah.
Right? So but remember we're dealing with cosine, right? So I
Yeah.
can't put 7. So how to be what we could do is pi on 3, I guess.
Yeah. Pi on 3 goes.
That'll be like 180, that'll be 60 degrees.
Mhm.
So we have, I think you had to pair everything Time minus here. Hopefully MATLAB not gonna cry. Right, okay. So let us analyze this before I run it because it may or may not work because MATLAB have a lot of very specific things in it. So we have a magnitude scale, which is the 5, right? Then we have a time scale, which is the 10.
Yeah.
We have a time reversal, which is the minus. And then we have a time shift. Yeah?
Yeah.
So let's look at the order. Let's make a nice acronym that we can memorize the order, because that's how I like to do it, right? So we have a magnitude, M, and we have a time, T. We can do, right? And then we have a reversal, so we can say R.
Yeah.
And then we have a shift, which is S. So a magnitude, scale, time, and then we have a reversal and a shift. Yeah, so that MTRS.
Yeah.
I don't know what acronym we could use. My technology. What else, right? What you could use for R? Relies. What we could use for R? That makes sense.
I don't really good at acronyms.
Oh, good. Okay, my technology really slow. Make
Yeah, that
sense?
works.
That's
Yeah.
simple. My technology really slow. Or you can say real slow. I'll go like the real, because that's how it does normally talk, right?
Mm-hmm.
My technology real slow. So my is magnitude. You probably write on this one time. T is your time scale.
Mm-hmm.
R is your reversal. And S is your shifts. Yeah,
Yeah.
look at that. We just got a nice acronym that you could use over and over with confidence. So you will know the order. So using this that we just got here, so let me analyze how MATLAB probably will look at this, right? So the first thing I will look at is the magnitude scale. So it will just increase the magnitude by 5, right? So let me
Yeah.
just sketch it before we actually do it. So we know just they have a sign, but we didn't reverse nothing yet, right? So it will be top is 5, bottom is minus 5. Agree?
Yes.
No problem. So the next thing, so we do the magnitude, done. Then we have the time scale, which is the 10, right? So
Mm-hmm.
the magnitude is still the same. So you say you're gonna add 10 more. Well, I'm gonna try to get 10, but something like that, right? It will just be more in the same period, right? Well, not period, but the same time slot, right? All right, so we have that. So that is the time scale, right? Then we had the time reversal. So it just mirror it in the x-axis, right?
Yeah.
So that means it would just look like this, right? Something like that, right?
Yeah.
Makes sense? All right, so that we did our reversal. Then we have our shift. So this shift is our shift 60 degrees, while we go into the left. Yeah? So, yeah, I agree, right? Going to the left. So it'll kind of look some like, if I was to extend this, probably might look like something like this. Yeah? And just how I analyze the signal. All right? Any questions on that?
No.
All right, well, let me see one if MATLAB will actually run this code for us. If not, we're gonna just move on to the past papers. All right, let's see. Yay! Oh, okay, it actually looking like a signal, but a lot of stuff happened to it. Yeah, he was crying. So let me just make it big. But yes, we see what happened in there, right? So everything we said happened. So the top is 5, all right? And then you have more oscillations in the same, and obviously somewhere here to shift it after we scale it. And yeah, it kind of looking like a even 2001 as yet, but it is what it is, right? It is what it's supposed to be. But you're correct. Everything I said there was correct. All right. Let me see if I do this. Oh, MATLAB Prime. Let's see if I do this. If I will change it. No, whatever. Yeah. Well done though. You seeing it now, right? You seeing it now. So I hope
Yeah.
the MATLAB helped to see what going on, all right? So any questions on those things? So we went through each of them, we went through the acronym to remember the order, and we saw how it will look physically with a signal. All right? So you could copy and paste those skills with anything on the face of the earth in the course. All right, so I can move on. Right. Nice. Here. Right. So I must clear this. Okay, so we just did that. Right. The next thing I want to do is special signals. So these are the main types of signals you will see coming up in this course, right? So the first one is a unit step. So that's denoted by U of t. So the piecewise for that is 0 when t is less than 0, and is 1 when t is more than or equal to 0. Hence the name unit. And it looks something like this. So yeah, different color. So this is t. So when t is less than 0 is 0. And at more than or equal to 0, it will shoot up to 1, and it will just stay 1 forever and ever, right? That's how it will. So as I call this a unit step. And this will apply to all the other laws that we learned before, the time reversal and all those things. So it'll still be the same, right? You can still use it for these things. All right, so that's the first one. The second one, all right, I missed one thing. You could use this for discrete signals also. So if you want to represent other discretes, it'll be U square bracket N of T close bracket. So we know a discrete signal, remember, is like pulses. So the same t is less than 0, and then it'll be 1, but t is more than or equal to 0. So it'll be the same graph, but instead of it being flat lines, it will just be pulses at 1. Yeah, that's how we'll look for a discrete signal. All right, so that's a step, a unit step. Right, so the second one is called a ramp. Right, so RT is what it is denoted by 0. So it's when t is less than 0 is 0. And when t is more than or equal to 0 is obeys t. So it does be t. So it does look like a linear graph. So 1, 1, 2, 2, 3, 3, 4, 4, y is equal to x. Right? So it'll look like this. So at 0, wherever it's starting, it will just shoot up like that. So that's our graph. All right. So we did the step, ramp, and the last one is some color impulse. So it's denoted by delta. Right. So it's just a unit impulse. So you normally call it a unit impulse. So this, just think of it goes to infinity. Right? But if it's a unit impulse, it will just stop at 1. So everywhere else on the graph, just made the line flatter, is 0, except at that specific point. So I'll repeat that one more time. Everywhere else will be 0, except at that specific point, right? So everywhere else will be 0, but like we say, normally at 0 will be the impulse, right? And it will just go up on the y-axis. Yeah, that's called data impulse, right? It's literally just an impulse. If I wanted to do, because we learned the operations, t plus 1, that means I'll have an impulse at minus 1. Because we just learned plus, there's a time shift. So it would just be here. If I wanted an impulse at positive 2, it will be minus 2. Yeah? So at 2, we have the impulse going. Same idea. That's why we did the function before, so you could see it going on here. So that is the impulse. So the three main ones, you have your, in order of importance, your impulse, your step, and your ramp. All right. So that's the main ones. And the last thing I have to show you is the order of operations. Well, order of operation, but in terms of differentiation and integration. So I'm going to draw this over. So there's an impulse at 0. All right, so there's that impulse. So that's good. So I have some coolers going, right? Because you have to integrate and differentiate and do different stuff with these signals. So I'll wait to remember this. I'll go and show you here. So we always start off with our impulse, right? Which on a graph, it would just be this. All right, so with our impulse, the cool thing about our impulse, should I write at the top, the area, or if you integrate our impulse, so the integral of this, so you can say the tau with respect to tau, is always 1. And there's something cool that is always true. So the integral of our impulse is 1. And 1 is a unit step, because it would just be a flat line. Yeah, so that's something cool to remember. So let's go back to this. So after the impulse, we have a step. And after a step, we have a ramp. I'm going to show you why this is important. So if I going forward, let's say when I going forward, I integrate. Because normally that's how it does add more. So let's go back to um add maths. If I integrate x without the other stuff, I'll get x squared. I know it have more to it, but don't worry. And if I integrate x squared, I'll get x cubed. And if I'm so on and so forth. So the same thing here, x squared, x cubed. But instead now we starting at 1. When I integrate 1, you're adding the x to it. And when I integrate it again, you will get the square to it. Same thing that happened in here. So this is like the 1, this is like the x, and so on and so forth. All right, yeah, that's integrated. So don't mix it up. So I'm gonna show you what I mean by that. You don't need to memorize the maths. It's just something to show you what will happen when you integrate. All right. So let's stop using this. Let's click this off. You're irritating me. All right. So when you integrate, so you go in this direction. What this means is the integral of our impulse is a step. So we know the step does look like this, a unit step, right? Like, so when you integrate an impulse, you get a step. If you integrate a step, you get a ramp. Yeah, so that's literally how it does go. Something cool. And then same thing if it was to go in the opposite direction. So if you're going in the opposite direction, you'll be differentiating, right? So it'll be differentiating. So if you differentiate a ramp, you get a step. If you differentiate a step, you get an impulse. And I saw the channel let us go and so give you questions as you see. When you tell it to integrate a function, differentiate a function, you just have to know, okay, if I integrate an impulse, I'm gonna get a step. If I integrate a step, get a ramp. If I differentiate a ramp, I'll get a step. If I differentiate a step, I'll get an impulse. Yeah, that's something cool for you to keep in the back of your mind when you do questions. So we did all that. I think I covered it. Okay, right. So I'll do one more thing, and then we could go to the questions, right? Do I have enough space to do that? Yeah, I'll just do it right here. So last thing on the list is some cool that I remember, right? Multiplication. So this sign here in maths, you know, it has multiplication, right?
Yeah.
But when you're doing signals and system, this is the symbol for convolution. So you have to be careful, right? Multiplication is different from convolution. So you have to know when you're multiplying something and you don't know when you're convoluting something. So just be careful with it. So we'll explain this more when he does the topic. Just keep in mind when you say a multiply is convolution, right? And then we know the dots is normal multiply.
Okay.
Right, so let me show you something. There's something called sampling, right? So example, I have this signal coming in. Yeah. So let's
Yeah.
name this signal P of T, right? Let's say I want to sample it. Sampling means, remember, when you're sampling something, you're trying to turn it into a discrete. So you're sampling it. Yeah. So sampling means every time you think of cars passing, every two cars that pass, you're going to read the color of it. So two cars pass, red, blue. You're just picking out at different points on the waveform, right? So if I multiply, you need to notice in multiply this, right? By a function I could sample it. And this specific function, the name of it is called a pulse train. It's just a train of pulses, as the word says. Right? Exactly as it says is what it is. So how a pulse trainers look, so put it down here. It's just a train of pulses. The equation for it is the sum from n equal to minus infinity to infinity of delta t minus n of t. That is the symbol of the representation of it. But how it does look is what more important, right? So it'll just look like a train of pulses. Now obviously you know it's one, right? Because it's a step. So just pulses, train of pulses. Yeah, that is all it is. A pulse, train, train, pulses, right? So since I go from minus infinity to infinity, it will include all these here, right?
Mm-hmm.
All right, so that's a pulse train. So I erasing this now, because I need the space. I'll add more slides in the next one. So we just learn what pulse train is. You'll see this in certain notes, right? So when you read through the notes, you will appreciate what I'm doing here more, right? I will urge you to read through the notes. I will send it to you if I need to. Just let me know. All right, so let's say we multiply this by a pulse train. So we know pulse train, that's a series of pulses. So I'll just keep the positive because I saw I have my signal here, right? What will happen is, so we can name this x at t if you want to. The pulse train to be x at t. If I was to multiply these two, so it'll be p at t multiplied by x at t. What will happen is these pulse train each pulse impulse, when I multiply by this signal, it will just fetch the value of P at t at that impulse time. So let's say it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. At 1, when you multiply it, it will just pick out the value of the signal at 1, 2, 3, let's say 4, 5, 6, 7, 8, 9, 10. Yeah? So when you multiply these two at 1 is here, right? So he will pick out that value. So I'm just plot it. I'll plot it at the bottom here as you go through. So you can see, right? So there's something important that you must know. So at 1, when you multiply it, this impulse will fetch the value at 1, right? So it will look like, and the height will represent the signal there, right? So that is that right there, right? Then at 2, it going quite up here, right? So the height will change, it fetching this value here. So it will look like this, right? Then at 3, it's kind of small, so it will look something like this here. Then at 4, it going down to here. So we'll go down to here. So there's 1, 2, 3, 4. Then at 5, where 5 is 5 here, it going down again, right? So 5 going down again. Then at 6, it kind of stopping. It fetching that value. At 7, it's going back up again. It probably catch it just by now, but 7 kind of lower. Okay, it fetching that value. So I can't draw it so high. So kind of be like right it. Then 8 going higher. You cannot catch it just by now. 9 is going down. 10 going down, and so on and so forth. So this will be the sample signal. So you could call this PRT underscore XRT. Yeah? So there's all this happen when you multiply a pulse train by a signal. It will sample at discrete times. So it does pick out the value at that specific time. That literally how it does work. Yeah, so you just end up with this. If you really trace it out, it will look like the signal, but it's just a discrete kind of representation of the signal. Okay, you sample it. Alright?
Oh,
So that's how it does work. So like multiplication. So anytime Sir give you a question and he multiplies something by an impulse, no matter what it is, it literally just go and fetch the value of that graph at that specific impulse time. So you say I have 2x and I multiply it by this. So Dirac t, this is at 0. Remember the default is at 0, right? You have to shift him from 0. So this, what this is, I just plug in 0 into this here. 2x. So it'll be 2 as 0, which is 0. It will fetch 0. If I was to do t plus 2, yeah? So t plus 2, it fetch any value of this, right? So you literally just go and plug 2 into this and you get end up with 4. And so on and so forth. It just go and fetch the value for it. That is the beauty of the impulse. So when you do a train of this, it will literally just do the same thing multiple times. Yeah? The less or the wider impulse train, the spaces in between it, is the less your signal, your sample signal will look like the original signal. But the more or the more compressed your pulse train is, it will look closer because you're kind of sampling up more intervals. Yeah? All right, so that was that. So that was the end of the introduction. So I did the functions, did it on MATLAB so you could see. I went through these special types of signals and I went through sampling so you could understand. Also, I went through the difference between multiplication and convolution in signals, right? So now we're jumping into the questions. So you need me to re-explain anything I went through there with fairly simple.
yeah, I think I got it.
All right, so let me jump into the questions. All right. All right, so I think I shared my whole screen still, so you should be able to see. Like that scroll along, obviously. All right, there you go. So you're seeing it, right?
Mm-hmm.
All right, I want to hide this. That's irritating me. All right, so you should be able to see it clearly, right? All right, so there you go. So we have a function and we multiply it by a impulse. Yeah. So when you multiply something by impulse, we just fetch the value at that specific point. Remember? So this here is at 0 because the value of it, remember this, let's make this a little smaller, is just an impulse at 0. So you have to time shift it to get different points, right? So if you wait at 1, you got to do plus, well, minus 1, and so on and so forth. All right? So there you go. So this one here, it does plug in 0 into the function. Remember, when you multiply by the impulse, it will just fetch the value at that specific point. Yeah? So this will be 3 as 0 squared plus 1, so that will just be 1, right?
Yeah.
Make sense? Remember the impulse just fetching the value of the function. That is what the impulse does, because that is what sampling is. All right, let's try this one here now. So we can make this here equal to 0 to get what t is. Yeah, we're trying to solve for t, right? That is basically why this was 0, because t, let's say plus 0 is equal to 0. So when you carry 0 across, t go equal to 0, right? Making sense? So in this one here, it could be t minus 1, you make it equal to 0. So t is 1, right? And that makes sense because remember, minus 1 is going to the right.
Yeah.
So technically, the impulse will be at 1. Makes sense, right? Because we just learned what right and left is with the signs. So we know you plug in 1 into this function we have here. So this will be 1 squared plus cos of 180 basically. So this will be 1. Cos of 180 is 1 minus 1. I don't know if I'm right or wrong on my calculator. I think cos of 180 should be, I don't want to use my calculator because I kind of lazy. That is half, right? So that should be minus 1. So I'm going to line in it. So that'll be 1 plus 1, which is like 2. Make sense? All right, so I gotta jump to this one. So this one, same thing. So 2t minus 2 is equal to 0. So t will be 1, right? So plug 1 into that. You're gonna put e to the minus 1, which is just 1 on e. So that. So you shift it, carrying multiply it. So either way, it's still gonna fetch the value here. So it's still gonna just fetch it. So they're just a glorified way of saying e to the 1. Anyway, and the last one. So this here we know is 0, right? So yeah, that's be e minus 2 as 0, which is e to the power 0, and anything to the power 0 is 1. And that is it. So all in all, the impulse, when they multiply, keyword I said multiply. When they multiply the impulse by a function, the impulse will just fetch the value of that signal at that impulse time. Yeah, that is all it is, right? That's basically it. And there's questions from your problems at one. All right, so that was that. So we're moving on. Look at how much space I left for that. And I didn't even start using it. Ooh, okay, nice. See you now? All right, so they want us to do some maths with this one, right? So they said to sketch the signal y at t x 2 minus t divided by 3, right? So with this, remember, we learned some functions, right? So we have to pick it apart to see what we have. And then we could do whatever we have to do, right? So we know my my technology rel slow. Like right now, this lagging. I gotta close up some tabs. Let's reshare the app. Reshare this. I'm probably sharing too much. I don't need all that. Alright. So it's still lagging. Let's exit some stuff. Don't need all this open, right? So processor heating up. Because I have too much stuff running at the same time. MATLAB will take up real memory. Like when I'm running, it does take up real memory. And it doesn't want to close. Anyway, you go close in your back. So anyway, so my technology rails, so we know the M is for the magnitude. My goodness. T is for your time. The R is for your reversal. You see in that log. And then this is the shifts. No. Right? You log in so much. Right? So we have those two going on. So looking at the question, right? We have 2 minus t on 3. Right? If it looking confusing, you could split it up in another way that kind of easier to look at. Right? So let's close up this. So look at it and let me know which functions we have there that we had to deal with. Take a look at it and see what we have. Remember, t is a variable, that is like x. So it's x of t, but the t have different operations going on. When you're ready, you could let me know. And I'll start.
Yeah.
All right. So we have 2.
Mm-hmm.
We have t, well, minus t. We have a 3. All right. So I'm gonna rewrite this in an easier way for me to see. So we have a minus t plus 2 all divided by 3. Yeah? So I'm just
Yeah.
rewrite this. So we could do a little bit of manipulation. So minus t on 3 plus 2 on 3. That makes sense. That will give us what we want. Will it? It should. Okay, shifting it by 1.5 and put a 1.5 and a 1/3. Yeah. Plus, okay, can't plus the 2 just so. Yeah, because that is not how it does work, really. All right, so let me see. So what we could do, we could say x minus 1/3 or t plus 2 on 3. So what we have a minus, which is a reversal, right? We have 1 on 3, which is a time scale, which would be a t. Then we have plus 2/3, which is a shift. Yeah. So all you're gonna do with this question here now, first thing you would do, come on, we have different orders, right? So we have t. So we had to do the time scale first. So basically I had to multiply everything here. So if it's 1/3, right? 1/3 is less than 1. So it should expand, right?
Yeah.
Probably. So if it's expanding, what you think you will do? You'll multiply the x values or you will divide the x values.
You would multiply.
So if I multiply it, it will just get wider, right?
Yeah.
Just get wide. And if I divide it, it should get small.
Mm-hmm.
Okay, so it'll be 2/3, then it will be 1/3, and the same thing on the next side, but that you sure that is well, yeah, it'll be expanded. Right, so that's the first thing, right? So you could probably do this when you're home, right? Because drawing it over and over is too much stress. So we did the time scale. The next thing on the list that we could do is the reversal, right? So all you're gonna do, remember already, time scale it, right? So you just reverse it. So this will just become on the next side, and you just redraw the shape. So you kind of like inverting it. So this will come up here. So it'd be some like, so if it flip, you go end up being here. And then this will end up being the next side with the thing going at the bottom. Yeah, so it kind of like flipping 180 degrees, because that's the reversal, right? And then the last thing we're gonna do is the time shift, which is the 2/3. So you're shifting it 2 on 3 So in this case, it's positive, right? So if it's positive, you're shifting it to the left. Yeah, so you just go and shift it 2/3 this direction when you finish. So after you time scale it and you reverse it, then you shift it. The shift is always the last thing that you would do. All right? And that's how it does break it down. Sorry, first in this question, they give you weird numbers, but small thing. So any questions on that?
No.
Take a look at it. Make sure you read it through, make sure I at least understand where I was going with it.
Yeah.
Right. So let me just teach you. No, it is wrong. But anyway, yeah, well done. So let you go through another one. Right. So that question you learn to use any laws and the order and applying it to a graph. In school, when Sid does it, obviously he will do it on the board and he will appreciate it more, right? That's really all it is. Yeah. All right. Let's see what's the next one. Okay, so this one here. I have a little bit of 2013 in this. You'll notice this semester, a lot of the courses will overlap, right? So some of
Yeah.
the stuff you do in 2013 will come back in signals and Laplace. Brush up on your Laplace, they do Laplace again, especially the partial fraction and all them things. Yeah,
Yeah.
that do it again this semester. So it will be in your best interest to brush up on your partial fraction for sure and brush up on how to do the Laplace transform and stuff. Okay, how to do it in signals again. All right.
Okay.
Anyway, so look at this question. So as always, we learn some laws, right? But let go through. So we have a graph, and they want us to show that the equation of the signal is this. So we have to break down this signal, right? So we have a 4, we have a 3, 500 pi t. So we know from 20 to now we could rewrite this in a better form, right? So we
Yeah.
could say A, but I'm gonna use A because that might confuse you. So B plus A sine 2 pi f t plus theta here.
Mm.
Looking familiar? All right,
Yep.
so in this case, B is our vertical shift, right? A, we know A is the magnitude scaling, right?
Mm-hmm.
2 pi f is where we get your frequency, which you can get a period from. And well,
Mm-hmm.
theta k is your, in this case, it wouldn't be a time shift, it will be a phase shift. That's a that shift loop. That's in the phase. Yeah?
Mm-hmm.
All right, so we have this going on, right? So let's go through. So B means is 4. But let me not start there. Let me do the same order that we learned before, right? So we know is sine function, we know it's a sine function, and it's a magnitude scale. So we know the top is 3 and the
Yeah.
bottom is -3. Yeah?
Yes.
So we know that for sure. Then time scale, we don't really have any time scale. We have a time, yeah. Well, I don't think we have it. Well, the 500, I guess would be that, but yeah, it's a time scale. So let me just equate these two. So we have 500 pi t, and that will equal to 2 pi ft. So the t's could cancel, and the pi will cancel, right? So you end up with 2f is 500, and f will be 250, something like that. That will,
Mm-hmm.
yeah, I think that's how it does go. Yeah, as much as I know. So that'll be a frequency. So 1 on that will give you a period, right?
Yeah.
Problem. So we go in somewhere. So let's keep that in mind. So where's 1 on 250? If I calculate a close by.
0.004.
All right. Well, I mean, that kind of finishing the puzzle. But if you look back up here, without looking at the vertical stuff, right? We know it starts in here, right?
Yeah.
Now look at that end in here, right? And the period is the time for one oscillation, right?
Yes.
Look at it, 0.04. So the first thing, right?
Yeah.
So you get the first part to say, you show them the how we do this here. Period is 250. Well, sorry, period is 1 on 250, 0.004 seconds. And you show them that the period for here, 0.04004, sorry, and the period here is 0.004 calculated. Yeah? So that is, you might get some marks, well, you will get marks for that. Anyway, so we have to put that. So you know this, the period is 0.004, right?
Yeah.
So we have any time reversals, no, right? I don't minus anyway, right? Have no minus inside here. See that? If it
Yeah.
had a minus outside, you could have do it. But you know the sign minus sine x is the same as sine of minus x. So you'll get away there. In this case, it have none. Time shift, in this case, is a phase shift, it have none, right?
Yeah.
So inside. So the last thing was that 4. So let me see if you remember. What course you will do that? I don't know if you remember one of the E-labs. You can remember what DC offset is?
Can't
No, yes, you
remember.
remember. So remember when you do the BJT,
Yeah.
you add a DC source,
Yeah.
the bias, and then you add a AC input.
Yeah.
Remember? So if you have, and when we learn what multiplying two signals is. So you have a AC coming and you have a DC that we say at 5 volts, right? What will happen is that AC will jump on to that carrier because it technically that way doing it carrying the signal, right? And it will jump onto it like this. So you will have a signal with a DC offset of 5. Yeah? So that's what
Okay.
DC offset is. I don't know if you remember the function generator. It had a knob for DC offset.
Yeah.
What I would do, it will kind of raise the signal up. The same signal, it will just be raised up. So instead of it starting at 0, it will start at whatever the carrier voltage is. So it kind of like riding on it. And then before you carry the output, they used to put a capacitor. Remember the capacitor? So that's a decoupling capacitor. So what that capacitor used to do, it will remove the DC component from the signal. So you will just end up with where you send. Well, just an amplified version, well, an inverted amplified version of it. Remember? I don't know if it's still fresh. So you just get amplified inverted without the DC. If you didn't put the capacitor, you'll end up with the amplified signal with the DC offset, which is not what you want. All right. So you just add a capacitor, and the capacitor will cancel out the DC, and you just end up with your AC signal amplified but inverted because of H bias. But this is what our DC offset is. So in this case, this +4 here, it will be a DC offset. So all that will happen is this 3 and the -3, it just going to raise up by 4, literally. So 3 going +4 and the -3 going +4. So -3 +4 is like 1. So the lower bound will be 1 now, and the upper bound will be 3 + 4, which is 7, right? 7.
Okay.
So if you look at the graph, you see it, 1, 7.
Mm-hmm.
Yeah. And that is it. I mean, and you show them the calculations with. So when you're doing this, you have to tell them, all right, have a DC offset of 4, therefore the bottom, well, the lower will increase by 4, up on it, lower will increase by 4. And you just show them this nice thing here. Remember, it's just one oscillation you do it for. Because everything is just going to be the same, because it's the same pattern being repeated. Yeah? So, and that's it. Same laws that we learned just now, just applying for physical question. And if you was to plot this in MATLAB, which I not gonna do, you'll hopefully get the same thing that I have here. Right? So the two major things, the period, the amplitude. Because if it's trigs, sine and cos, like based like most likely the most important thing that I have, the period and the amplitude. Whether I could get with like everything in. All right. All right. Any questions on that?
No.
All right. See you less. I see how the 2013 knowledge has come in handy. All right. So we have this question here. So there's a past paper question. Same idea, right? You'll see the same that I show you with the differential and the integration thing is where this has come in handy. So you have input signal x at t. So x at t is this signal here. Yeah, same graph. And then blah, blah, blah. So the operations are the derivative operation, a time amplitude operation, and a multiplication operation, right? So A, B, and C. So the first thing I want us to do is differentiate it, right?
Yeah.
Then they want us to do some operations, and then they want us to sample it, which is this. Anytime you see this sum minus 2 to 2 of this, there's just a pulse stream. So, and we just learn when you multiply a pulse stream by something, it will just pick out the value at that specific pulse interval, right? So don't get shocked when you see this. And going from minus 2 to 2, right? Okay. Right, so let's see, let me differentiate this. So when you differentiate, and that's what I like to do, obviously, because I'm sketching it here. The same time we learned just now, the order. When you differentiate, so the impulse step ramp. When you differentiate a ramp, you get a step. When you differentiate a step, you get a impulse. Yeah? So what I like to do is draw a line so you can separate the different pieces. So it should be on the same scale, right? So we redraw the scale after. But that's what I like to do. So you can literally see the different pieces. Ultra. Might have to go down more. Do I should have enough space? There's our sketch. So don't beat me up with the graphing looking too similar. All right. So there you go. So we have this first piece. So we start in here, right? And we jumping onto the thing. So this side is go around. So the first time we jump on here, we going up. Oh, that's that impulse, right?
Yeah.
No problem. So keep it in mind. So we want to differentiate impulse. You don't know. You just lost. All right. So with that said, you just keep that as how it is. All right. So just at minus 2, you go and apply that. All right. Just keep it as that. If you're going up, you're going up. You can't really do anything about it. Because it have nothing before impulse. Yeah. And also, little rule, remember. So you have this. So dt is equal to 1 from minus infinity to infinity, right? So if you integrate a impulse, you get 1. So if I was to differentiate this, wouldn't it just cancel the integral and you'll
Yeah.
just end up with 1? That makes sense?
Yeah.
Yeah, sure, that makes sense.
Yeah,
Because
that makes sense.
integral is 1, if you differentiate, it will cancel, so you end 1. Yeah? Alright, so you
Yeah.
notice at 1. So I'll draw a little sketch for the x-axis, or the y-axis, that would be. So there's that 1, right? Alright, so that's done. So we're here now, right? So we have this piece here, which is our ramp. Yeah, when you differentiate our ramp, you get a step.
Yeah.
Okay, so that will just look like this, right? All right. So now the next thing we have to do, we here now, we're going down. So down is a negative gradient. Remember, basically, we're trying to get here is the gradient, right? So
Yeah.
if you're going down, that is a negative gradient. So you can't draw that here. You can't go across here. That would be wrong, right? Okay, it had a map. So you had to go at the bottom. So I had to extend it down a little bit and draw your thing going across here, right? So disconnect. All right. Okay, so nice. So we have that going there, good. So where we at now? We here. So now we have the same thing, shooting up to here. So we just gonna do the same thing. Shoot up and shoot up. Barely do anything about that. All right, so I'm gonna use a different color. So we're shooting up from there. So because the intro is 1. So we had to shoot up, we can shoot up too. Because how I draw this, it kind of hard to see what's what. So that shoot up is like what, 2? So should shoot up to like right here. Because that is 0. There's 1. So that is that. So now we're here now. So there's our step. So when you differentiate our step, you're supposed to get an impulse. So that is this period here. So there's a step here, right?
Yeah.
See that? And this going down to the next piece. So when you differentiate a step, you get impulse. All right, so we like the impulse at 1, and you have a ramp. So we do the other pieces for now. So when you differentiate a ramp, you get a step. So this piece here is going down. So you know it's negative. So it'll be here. All right, and then you have this piece here going down because it'll be going down, right? So that's our impulse going down. So I'm gonna show you something. If I have a flat line, the gradient is constant, right? Which is like 2.
Yeah.
So if I differentiate that, it wouldn't get 0 because technically it was not there anymore.
Yeah.
So technically I can't really draw anything to represent 0,
Mhm.
which so I could just leave it blank. That makes sense, right?
Yeah.
That's why I didn't write anything for this and this. I need to write something for this going down. So I had to write an impulse going down. Then you have the ramp, then nothing, and then the impulse. That makes sense. Sure, that makes sense to you. Sure,
Yes.
sure. So a ramp, so yeah, first you're going up, impulse, ramp, step. Down ramp, negative, step. Impulse, you go straight up, impulse. Horizontal line, the gradient of a horizontal line is nothing. Yeah? Then you're going down, so impulse going down. Ramp, step. Nothing, which is basically 0 right here. Nothing, right? Then your impulse going down, impulse. And that's story. Fair enough? So you have to remember.
Yes.
Impulse, step, ramp. If you start at the end, if you differentiate a ramp, you get a step. If you differentiate a step, you get impulse. All right? Going forward is integrating, right? So if you're going back, it will be differentiated. Fair enough?
Yeah.
All right, no problem. We just following the pattern that the question gave you. So impulse up to 1, impulse going up. Ramp, ramp. Negative ramp, negative step. Impulse, impulse. All right, then you have nothing to nothing. Going down, impulse. Ramp, step. Horizontal line, nothing. Negative, negative impulse. End of story. Yeah, you're always
Okay.
going in that general direction, right?
Uh-huh.
So we'll let you know what is a positive impulse and negative impulse. Okay?
Yeah.
Alright. So that was that. So that is like our typical pass rate. Alright. The next thing we will do, we will stop at C and you can try the rest because the rest is just basically the same thing. And I will show you some with this. And you can try the rest. Should be good practice, especially this one. And at the end of the paper. Right? So let's run through this. So the second thing they want us to do here, obviously you could try this. I'm not gonna draw this over. All right. So we have 2 here, right? So that there's a magnitude scaling, right? So we just learned that. Yeah. Cut outside. So that magnitude. So that is M, right?
Yeah.
Then you have a minus, which is a reversal. Then you have a half, because 1 and 2 is a half, right? So
Uh-huh.
that there's a time scale, right? So and then there's 2 here as a shift. So we have and this here. So we have this here as a what else? A T time scale. Then you have a R reversal. Then you have a shift and a magnitude scale. So we have these things going on here. So the first thing we will do is a magnitude scale, which just go and multiply the whole thing by 2 in this case, right? So 3, 6, 2, 4, 1, 2, everything go and just increase. So what I do, just draw by the same shape and change the y values. Simple, right? So just go
Yeah.
and it growing, right? So that is M done. The next thing we have to do, and so that is my technology rails, so my T. So we have to do the time. Yeah. So in this case, B is less than 1. So it should expand. So it should get bigger. Yeah. So it will get bigger by a factor of a half. Let me make sense of this, right? So if I have a graph at 1, yeah, and I said f of x. If I do f of 2x, right? This graph here, since 2 is more, it will be compressed, right? So if I was to multiply this by 2, do you think that will be a compression or expansion? Note I
Uh,
multiply there, right? I multiply by 2 there.
right. That would be a compression.
You sure that'll be a compression? Before it was 1. You tell me that if I multiply by 2 and get 2 here, think that'll be, remember there's 1 here. Now without 2. So you think that'll be a compression or expansion?
I think it'd be a compression.
But when it compression, you get more. It not looking like I gain more here. I gain less. Come, but there's still 1. Now I had the
Uh,
same thing, but it ended at 2 now.
okay, so then
That's
that'd be the
more.
expansion.
Nah, you see, you've visually seen it now, right?
Yeah.
So in this case now, it expand. So when you expand, you multiply. So if I was to do f of 1 on 2 of x, that is it less. I just looking at how the maths will make sense, right? So based on that, if we look back at the question that we're doing, t on 2, basically a half, right, is less than 1. So you're supposed to expand. So we should, if we multiply by a half, look at the values, right? If we multiply this by a half, this will be 0.5, right? This will turn to 1. And this will turn to like 1.5. Remember, you still have 2.5, and then you have 3. So technically, you could have redraw a whole new pattern with it. But that wouldn't make any sense. Seeing that, right? Because
Yeah.
if I multiply, it looking like I could draw a whole new pattern with it again. We'll just show it. Cause let us know, get confused with it. So like I could do this, shoot up, come across, and do my whole chalala and get a new pattern. So that's a multiply here, right? I multiply together. But that looking like I get 2 in the same space. Come on, by what it ended at 3 just now. So you
Yeah.
think multiplying can give us what we want to achieve if we know it's less than 1. So we know it had to be an expansion, right?
Yeah.
So it had to look like it expand. Yeah. So
Yeah.
to get what we want, we got to divide. So when we
Okay.
divide, look how go. So when you divide everything, it will flip. Remember the flip? So you basically kind of like multiplying by 2 in this case, right? So this will go to 2. You understand that, right? That makes sense. If
Yeah.
I divide 1 divided by half, the 1 multiplied by the reciprocal, you get 2. So it's the same thing as you're multiplying by 2, right? So this will be 2, and this will turn to 4, and this will turn to 6. And that looking like an expansion now. Okay,
Yeah.
get bigger. Yeah?
Mm.
So now this used to be 3, right? And but now look at it, and again, less of the piece. So it get bigger. So in the same window, you're seeing less of it.
Yeah.
That makes sense. Sure, that makes sense. So a lot of students are saying, oh, expand, multiply, compress, divide, and get it wrong. Yeah, I don't want that to be you. So what we learned just now is that when you're expanding, you just do the opposite of what you think conceptually you will mean. So when you're expanding, you divide. And when you compress, you multiply. Yeah, that's just the train of thought. If you're confused by that, just look at the graph. You know, the one thing you have to know, B is less than 1. So you know it have to expand, how to look like an expansion. So you do with a couple points, you multiply and see how it looking. And you know how it will look if it expand and if it compress. And with that, you will know if you had a multiply or divide. Feel safe. Yeah, instead of just multiplying, remembering something hard fast, look and see how it will look on the paper. That's what we better thing to do. All right. So we look at that. We'll like get our whole question wrong if we had go and multiply. See that?
Yeah.
So let's look at the maths, try the maths with the values and see if it makes sense visually. All right. So that was how did we do everything? No, we had just did we did just the time scale. Yeah, we did the time scale. So the next thing we have to do is the time reversal. All the time reversal is just gonna flip. Rotate 180 degrees. The end will become the beginning, right? That's what we have. Just inverts. It's a time reversal. Yeah.
Yeah.
And then you just and you shift it by 2. In this case, it'll be plus 2. So that means it will shift to the left. So you just go and shift your whole thing you do have the magnitude, the time shift, the time scale, sorry, the reversal, and you just shift it 2 spaces to the left. And you're done.
Okay.
Because the last thing you just do, the time shift. Yeah? So that is the
Yeah.
last thing you always do. Because my technology real slow. Yeah? So we did everything in the order we need to do. And the last thing is the sampling thing. All right, so all this is you're going from -2 to 2 now. So remember, you shift the graph. So because you shift the graph 2 spaces, you have negative values and some up. So basically, let's say you're going from -2 to 2. So -2, -1, 0, 1, and 2. And you just fetch the value of the graph at that point.
Okay.
Yeah, and you just redraw the x-axis, the y-axis, and you just draw the heights of the impulse, and you can just put the value on top of it. Yeah, and that is what it do. The sample. Just fetching the value at the particular point of the impulse. Fair enough? So so like say if I had to sample this current graph here, note that I didn't do any shift or anything to it, right? If I was to sample it at -2, it will go up to here. So that'll be an impulse. -1 will be here. At 0, so at 0 we're going, it should be right here. Remember it fetching the value, right? Then at 1, it's right here. Should it? And then 2, it's stop here. So that'll be your sample. There you get it. Yeah, that's a sample. And then, so this one here, you could just show you some. So this, you should be able to sketch these things. So u of minus t. So it'll be u of 1 minus t. So just apply the laws in the order. So you have a reversal and you have a time shifts. So you do the reversal. So you know this is u of t. Oh, we'll start with the standard, right? And then you reverse that. So if I reverse it, it will just be in the opposite direction, right?
Yeah.
And then plus one, that means it's shifting to the left, right? Because this here is like minus t plus one, right? If you just flip it. So that means it's shifting to minus one, and it will just be like this, right? So that's how it will. And then the multiplying it by x of t. So basically what will happen is because everything else here is zero, you literally just multiplying the points by because it's multiplication. So if I draw in it, so ut you have one, if you invert it, and you have one, where that will give. So it should be, that's not it. Minus t u of one. Oh, right. That is what I do. So let's put it at one first, and then reverse it. So u of one, and then you flip it, you should put this. Because basically what we had just now, we didn't get nothing. Come on, what is our step? Right, so you have u of minus t plus one. Right, this plus one here, it will be here. So technically, how Sir gave you this question here, you will confuse everybody. So if we obey the laws that we did, the reversal is before the time shift. So if I reverse this, you should end up with this.
Okay.
Yeah? And then if I
Yeah.
shift this plus one, you will just literally just end up with it looking like this. Yeah? So if you multiply this by this here, you ain't gonna get nothing. Yeah? So it will be empty. Yeah? So that is it. That is that one. Another trick in that question is if you apply the same law, you'll like get that question wrong. Yeah? So that was
Yeah.
that. And then the other one now, I just use them a lot because sometimes I will notice that solutions will have a lot of, it will have mistakes in it. And it will kind of throw you off because you'll be like, buying again that. Yes, so solution does have mistakes in it. A lot of mistakes. Yeah? So
Yeah.
they'll be too flustered when you don't get what they have. Anyway, last one, you have this here, URT. So we know how URT will look, right? Then we have subtract URT, so minus one. So all right, so URT minus one, right? So we know that will be one, yeah?
Yeah.
And then have no reversal there. So it'll just be here, right? We cannot overlap. So if you subtract those two from each other, it will be just left with this piece here, right? Make sense?
Yeah.
You sure?
Yeah, that makes sense.
Okay, you're subtracting this piece from the bigger piece. But the red start before and the yellow after. So if you subtract the yellow from the red, this piece here will disappear, right? Yeah? So now you're multiplying this here by this here. So basically that's going to end up with this become, and we just multiply the values by it. So 1 by 1 is 1, and obviously that's end. So this will be the answer for that piece. Yeah? Remember, this step is a unit step. So that's 1, right? So when I multiply the two, 1 by 1 is 1. So it literally going to be the same. Yeah? And
Yeah.
that's it. And obviously you could do this by yourself. Find the d value, x at t, just find wherever that 3 and 2 is, 1.5, that should be right there. And you're done there, right? You can try this one, same thing I showed you just now. The differentiation, you start here, you start to walk, go down the road, and you finish. Remember, when things negative, we had to draw it negatively, right? Remember, it's gradient. Differentiation is give a gradient. right? Gradient have a negative slope, it's negative, so on and so forth. All right, so that'll be the end for that. Any questions or anything added?
No.
All right, so with that, let me just stop the recording. Right, so you have our start.